Okay, let's look at problem set 28. This is again in chapter 10, problems 10, 12, and 14, so you won't find the answers to these problems in the back of the book. Um, let's start with problem 10. Problem 10 is a very fundamental problem. You have a lake of fresh water, and you know that the density of water is 1, okay? And that makes it really easy to work with. And of course, that's how we define the gram, is a gram of water is the amount of water that takes up 1 centimeter cubed. And we're told that we have a rock. Well, we're told it's a ball, but the density of it looks pretty much like a rock. And this ball has a mass of 400 grams and a volume of 100 cc's. Now, the density of that ball is going to be the mass of the ball divided by the volume of the ball. And that's going to be 400 grams divided by 100 cc, or 4 grams per cc. And so you know that that ball, rock, has a density 4 times that of water, and so it's going to sink like a rock, okay? Because that's what it's made of. Now, the first part of this problem asks us to find the buoyant force. And there's more than one way to spell buoyant, I assure you. But Archimedes taught us that the buoyant force is equal to the weight of the fluid displaced by the object. Now let's parse that. What does that mean? Well, where that rock is now, water used to be, okay? And the buoyant force is going to equal the amount of water that was pushed out of the way. If you would take that amount of water and put it on a scale and weigh it, that would be the buoyant force, okay? And we explained in lecture what Archimedes used for reasoning to come up with that. Okay, so what we want to do is we want to think about the amount of water that is displaced by that rock. And what you could do in your mind is create a duplicate of that rock, the same size and shape, but make it a rock out of water. Okay? Now, that rock of water has a certain weight force and a certain buoyant force. And because that ball is made out of water and it's no different than the neighbor water, it's not special. It's not going to go up, it's not going to go down, it's just going to sit there with its neighbors. So that means whatever the weight of this ball of water is going to be the buoyant force on that ball. And because of the same size and shape, surrounded by the same amount of water, pushing the same amount, that's going to give me the buoyant force on the block. In other words, this is equal to that. And by Newton's second law with zero acceleration, this is equal to that. Well, let's find out what that is. Well, I know that the volume of this ball is still going to be 100 cc's. Well, this is going to be the mass of the water times G. Well, what's the mass of 100 cc's of water? Well, that's where this density of water comes in. That makes water so easy to work with. We have 1 gram for each centimeter cubed, or cc. cc stands for centimeter cubed, okay? And so if I've got 100 cc's and each one of them has a mass of 1 gram, I've got to have 100 grams of water. And then G, of course, is just 10 newtons for each kilogram. Now I hope you see a problem, because there is a problem. And that is, I'm not going to get a force in newtons if I've got grams here and kilograms there, okay? When you're dealing with buoyant forces, you're always going to have to convert this mass of the ball of water into kilograms. And so this is going to be 0.1 kilograms times 10 newtons for each kilogram, or 1 newton, okay? So that means this buoyant force must be 1 newton, which means that this buoyant force must be 1 newton. So the buoyant force on the rock is 1 newton. Now, part B asks us to find the acceleration of the rock. Well, I know the direction is down, and that's because the weight force of this rock is going to be bigger than 1 newton. How big? Well, I've got 400 grams for the mass, and I've got to write that as 0.4 kilograms times 10 newtons for each kilogram, and that's going to be 4 newtons. So if I look at this free body diagram, I got 4 newtons down and 1 newton buoyant force up. If I use F net equals MA, my net force, if I've got 4 newtons down and 3 newtons up, well, I didn't say that right, did I? If I've got 4 newtons down and only 1 newton up, my net force is going to be 3 newtons down. And that's going to equal the mass of 0.4 kilograms times the acceleration. And that's going to give me an acceleration of 3 newtons down divided by 0.4 kilograms, and that's going to be 7.5 meters per second squared down. Okay? Talk to your neighbor, or not, or socially isolated. Okay, so the answer to B is 7.5 meters per second squared down. Okay, let's look at problem 12. Let me just pause here and point out that there's a formula in the book. I didn't want it to be in the book, but it is in the book. And that is that the buoyant force is equal to rho g volume. Well, that formula is true, but if used incorrectly, it's going to give you an answer that's 1,000 times too big every time. And that's because we tend to use densities that are in units of grams per centimeter cubed, because it's so handy to work with liquids with those units. And G is in MKS units, meters per second squared or newtons per kilogram. And so I would prefer that you not use that equation. If you have to use that equation, use it this way. Rho volume and then times G. And the density times the volume is going to give you a mass. But before you multiply that mass by G, you better figure out, you better convert it to kilograms. Usually if this is grams per centimeter cubed and this is centimeter cubed, this is going to give you grams, like we got here, okay? We got 100 grams, and then we had to convert it to kilograms before we could multiply by G. Okay, in my mind, it's safest just to imagine a ball or a shape of water that's exactly the same size and shape of your submerged object, and just ask yourself, how much does that weigh? Okay, I hope that was helpful. Let's go to problem 12. Okay, in problem 12, we are told that we have a block of unknown material, and the mass of that block, let's just write it as M, is 18 grams. And the volume of that block is 20 centimeters cubed. And that's going to give me the density of that block, which is just the mass of the block divided by the volume of the block. And that's going to be 18 grams divided by 20 centimeters cubed, and that's going to be 0.9 grams per centimeter cubed. And that's part A. And now we're told that we've got two buckets. We have a bucket of water and a bucket of alcohol. And these buckets are filled right to the brim. Okay? Right up to the brim. And the density of water is 1 gram per centimeter cubed, and the density of alcohol is 0.79 grams per centimeter cubed. So part B asks, what's this block going to do if I put it in these two buckets? Well, because the density of the block is less than the density of water, that block is going to float in the water. But because it has a density greater than that of alcohol, it's going to sink to the bottom of the alcohol. Now we're asked in problem 12, if I place it slowly and carefully in the bucket of water, how many cc's of water will be spilled out? Well, when something floats, there's only two forces on it. There's the weight force, the earth acting on the block, and this buoyant force, which is equal to the weight of the liquid displaced. Okay? Well, the weight of the block is just the mass of the block times g, and the weight of the liquid displaced is just the mass of the liquid displaced, spelled with a Q, times g. Well, if this block is just floating there, it has no acceleration. So by Newton's second law with zero acceleration, these two forces have to be equal to each other. And if they're equal to each other, that means the mass of the block times g is equal to the mass of the liquid displaced times g. And if I cancel out the g's, I see that the amount of liquid that is displaced when something floats is equal to its own mass. In class, we had the example of the 10-ton ship. If it's going to float, it's got to displace or move out of the way 10 tons of fluid. Now, this is water, so what we know is that when we, and also we filled up the bucket all the way to the brim. So when we displace water in a bucket that's already full to the brim, what that does is it causes water to be spilled. And so I get a puddle here. And the question is, how many cc's of water are in my puddle? Well, I know that the block has a mass of 18 grams. And since the mass of the block is equal to the mass of the liquid that gets pushed out of the bucket, this is going to be 18 grams of water. But we were asked how many cc's, how many cubic centimeters of water. Well, water is just really easy to work with because it has 1 gram for each centimeter cubed. So this would also be 18 centimeters cubed. So there's 18 centimeters cubed of water spilled on the table. Now in the alcohol, the block actually is submerged. And so that means where the block is now, alcohol used to be. The whole volume of that block is pushing alcohol out of the way. So my puddle of alcohol here is going to be equal to the volume of the block, or 20 cc's. So those are really important tools to have in your toolbox. When something floats, it displaces an amount of liquid equal to its own, it displaces an amount of liquid equal to its own mass. When something sinks, it displaces an amount of liquid equal to its own volume. Okay? So let's see. B was saying that it floats here and sinks there. This was part C, and this was part D. Now part E said if you had a 37-gram chunk of this same material that we made the block out of, what would its volume be? So for E, we just use the density equation. Okay, and I'm just going to cross multiply here and say that the volume is going to equal the mass divided by the density. Okay, so here we're told that we have a 37-gram piece, and this has a density of 0.9 grams per centimeter cubed, and that's going to give me 41.1 centimeters cubed. Okay. Okie dokie. Let's go on to the last problem. So in the last problem, we have a table. Um, Actually, let's start with the buckets. We've got 3 buckets with liquid X, liquid Y, and liquid Z. And we have a ball of clay. And the volume of the ball is 5 centimeters cubed. And we have a table okay, and this is liquid X, liquid Y, and liquid Z. And in this table, we lower the ball into each of the beakers, and the beakers start out filled to the brim, and we measure the mass and volume of the liquid that spills over the edge. And so this is going to be the mass of the fluid displaced. And this is going to be the volume of the fluid displaced. And this is just, does it sink or does it float? Well, we're told that the mass of the liquid displaced is going to be 4 grams. Oops, got it wrong. 3 grams and 6 grams. And the volume displaced is 5 centimeters cubed, 5 centimeters cubed, and 3 centimeters cubed. And the first part of this problem asks us, in which of the beakers does it sink and which does it float? Well, I notice that the ball has a volume of 5 centimeters cubed, and in liquid X and liquid Y, it pushes out of the way or displaces 5 centimeters cubed. And so that means that this ball must sink in X and sink in Z. And that's going to give me these puddles. Okay, and this puddle is going to be 4 grams and 5 centimeters cubed. And this puddle is going to be, spelled Y wrong. Okay. This is going to be 3 grams and 5 centimeters cubed. And then if we look at, so it must sink here and sink here. But if we look at liquid Z, only 3 centimeters cubed of liquid have been displaced. And the ball takes up more space than that. So that means that this ball must be floating with 3 centimeters cubed below the surface and 2 centimeters cubed above the surface. And that's going to give me a puddle that is 3 centimeters cubed and 6 grams. Now, that's the first part. The second part asks us to use the information in the table above to find 2 things. The mass of the ball and the density of the ball. Well, there's 2 ways to go about this, okay? Let's let's go about it the kind of the forward way. Um, when I'm looking for the mass of something, I look for an experiment where it floats. And that's this experiment here. When it floats, I only have the weight of the ball, which is the mass of the ball times g, and the buoyant force, which is equal to the mass of liquid z displaced times g. And because it's not going anywhere, it has no acceleration, these two must be equal to each other. So the mass of the ball has to equal the mass of liquid z displaced, which is 6 grams. Now the density is just going to be the mass of the ball divided by the volume of the ball. Well, that's going to be 6 grams divided by 5 centimeters cubed, or 1.2 grams per centimeter cubed. That's one way to solve that problem. There's another way. In class, we found that if you could only see 10% of the iceberg, that means 90% of the iceberg is submerged. And we were able to show in class that that means that the density of the ice is 90% of the density of the water that it's floating in. Well, let's use that here. What fraction, what percent of that ball is submerged in liquid Z? Well, the percent submerged is going to be 3 centimeters divided by the total of 5 centimeters. So that means that if I do 3 over 5, that's going to be 60% is submerged. Okay? And so that means that the density of the ball is going to be 60% of the density of liquid Z. Well, I found out when I gave that calculate your grade little recipe that some of you don't know how to deal with percents. Well, 50% is just a half, right? And so I could say that 50% is equal to 0.5. So if you've got a percent, you just move the decimal place over 2 places to the left. So this is going to be 0.6 times the density of liquid Z. Well, I can find the density of liquid Z by just looking at the puddle I have on the side of this bucket. The density of liquid Z is going to be the amount of grams that were spilled divided by the number of cc's that were spilled, and that's going to be 2 grams per cc. So if I take 0.6 times 2 grams per centimeters cubed, that's going to give me the 1.2 grams per centimeter cubed, which is the same answer we got going this way. It's like dancing. You can dance forward or you can dance backwards, unless you're a guy. Okay, so let's go forward and see what's on the next page. Sometimes these problems get broken up here. Which of the 3 fluids exert the smallest buoyant force on the ball of clay? Well, that's easy. The buoyant force, whether something sinks or whether it floats, doesn't matter. The buoyant force is always, by Archimedes' principle, equal to the weight of the fluid displaced. Okay? So, C, the buoyant force is equal to the weight of the fluid displaced. Well, that's equal to the mass of the fluid displaced times G. Well, G is just 9.8, call it 10 newtons for each kilogram, always. So the biggest buoyant force is going to be the one that has the biggest mass displaced, and the smallest buoyant force is going to be the one that has the smallest mass displaced. So liquid Y is going to exert the smallest buoyant force on the block because it displaced the fewest number of grams. Okay, the last part of this problem asks us how much extra clay in centimeters cubed would you have to add to increase the mass of the ball by 4 grams? This is just exactly the same as the last part of problem 10. It's kind of boring, and it's just the volume is going to be the mass divided by the density. I want to increase it by, oops, got the wrong page here. 12. Oh, no, I had the right page. Oh, I'm getting this wrong. To increase the mass of the ball by 4 grams. Okay, so we want to add 4 grams, and that is a density of 1.2 grams per centimeter cubed, and that's going to give me 3.3 centimeters cubed. Sorry for the delay there. I lost my place. Okay, my friends, that's problem 14. And that's the end of homework set number 28. Okay, locked out.